Hello folks, so last time we looked at 3 theorems on circles, especially, theorems related to chords. And if we can quickly summarize that before we move on to the new ones, okay? Let me share my screen. Okay, so the first 2 theorems were about equal chords, right? If there were equal chords in the same circle or congruent circles, I think that was important, either the same circle or congruent circles, then we saw that it swept equal arcs, right? So equal chords contain equal arcs. We proved this, and the converse of this is also true, right, guys? Which means that if we saw there were 2 equal arcs in the same circle or congruent circles, then they in turn contained equal chords. So we looked at both of these, and then we looked at another important theorem which talks about a line that is perpendicular to the chord, a line that is perpendicular to a chord from the center of a circle bisects the chord. I think this is one of the very important outcomes. A line that is perpendicular to a chord from the center, not any other point, but from the center of the circle to the chord, then it bisects the chord. Right, guys? And we also saw that the converse of this is also true. What could the converse be? The converse of this theorem is if we see that a line is indeed bisecting a chord, and that line happens to be from the center of the circle to the chord, right? So I have a chord somewhere here, and we see that there is a line from the center of the circle which is bisecting the chord, then we can very confidently say that this line is perpendicular to the chord. So the converse of both of these is what we looked at. And we also worked on a few scenarios where we could apply each of these theorems, right? So shall we now look at other theorems with respect to chords? So here we are, there is a circle, the beautiful symmetrical shape. We have a circle, O is the center of this circle. Let's now look at properties of equal chords, okay? So let's say there is a chord AB and there is a chord CD. These 2 chords are equal. Now, if you connect the endpoints of the chord to the center of the circle, what is your observation, especially with respect to the angles? I'm going to write somewhere here in the corner. What is your observation with respect to the angle AOB and angle COD? Because these are the central angles of the chord, right? What can you say about them? Don't you realize that these 2 angles are equal, which means equal chords subtend equal angles at the center. But yes, this is not a postulate, it's a theorem. So shall we take a moment to prove this, guys? Or would you rather want to pause the video, try and prove it yourself? Okay, if you would like to do that, please pause, try, and then verify. Cool. Okay, let's assume you've tried it on your own. So very clearly we have 2 triangles here. Okay, before we even write all of this, shall we just make a note of what needs to be proved and what is given, right? So what is given is we have 2 equal chords, right? So chords AB and CD are equal. And as always, I ask you to mark what is given in the diagram, because a diagram speaks 1,000 words, right? What do we need to prove, guys? We need to prove that angle AOB is equal to angle COD, because we are talking about the angles subtended at the center are equal. Okay, let's jump on to the proof. Now here, the first thing we will do is we'll join OA, OB, OC, and OD. So it forms two beautiful triangles. Let's see if these two triangles are congruent. Triangle AOB and triangle COD. What can you say about the sides? We definitely know that AB is equal to CD, right guys? This is given. Then you can see that AO is equal to BO is equal to OD is equal to OC, because they are the radii of the circle. So you have AO equals OC, and we have OB equals OD. All the four are radii of the circle, right? So here, by the SSS postulate or criteria for congruence, we can say that triangle AOB is congruent to triangle COD. This is a very quick one, right, guys? Therefore, by CPCTC, right? Corresponding parts of congruent triangles are congruent. We use this acronym very often if you are from the CBSE or ICSE board. Otherwise, you can just say as an outcome of two triangles being congruent, corresponding parts are equal. You can mention that. Otherwise, this would suffice. By CPCTC, can we say that angle AOB is equal to angle COD? Therefore, equal chords subtend equal angles at the center. Right, guys? Equal chords subtend equal angles at the center. Very easy. Now, I have a small request to you guys. See, if our diagram to prove this were slightly different, let's say we have a circle and we have taken two chords that are perfectly parallel to each other and they're equal, okay? So we've taken two equal chords on either side of the center and the ones that are parallel. And then if you happen to join them, let's join them, something like this, you will observe that these two central angles appear as vertically opposite angles, right? Vertically opposite angles. Now, if you draw your diagram in this manner, then you could you would be tempted to use the SAS postulate, right? You pick the radii, or you don't need to do anything. You can actually conclude that, look, I see that these two are vertically opposite angles and hence the central angles of the chords are equal, right? But if you do that, you're not covering every single case of chords being equal anywhere in the circle. Hence, you should try and avoid such proofs, okay? Whereas if you pick something like this, you can move the chords around anywhere in the circle, but they need to be equal, and still use this postulate, the SSS postulate, to prove that they're congruent, okay? So just be mindful when we're talking about a theorem or we're proving a very generic case, we should try and avoid proofs that only cover certain scenarios, okay? We should try and avoid proofs that only cover certain scenarios, and instead our proof should always apply to all scenarios, okay guys? Fantastic. So let's move on to the next theorem, which could be the converse of this, right? Every time we prove something, we want to check if the converse of this is true. What could the converse of this be, guys? So we started with the circle we checked if the chords are equal, are the central angles equal? Am I right? Now, the converse of this could be that we begin with the fact that the central angles of the chords are equal, and then we check, whether the chords themselves are equal or not. Okay, so the statement goes like this: if two chords subtend equal angles at the center, then the chords are equal. Well, I'm making the statement. It is indeed true. Can you try and prove this? So in this case, given, we first begin with the fact that angle AOB is equal to angle COD, right? We start with this. Whereas you need to prove, by the way, we have this, and we also have that AB and CD are chords. Oops, sorry, hang in there a bit. AB and CD are chords. And we need to prove that AB is equal to CD. Can you pause and try it on your own, folks? Okay. Okay, assuming you just guessed the postulate, which you could use to prove. Let's first join OA, OB, OC, and OD. Right after that, everything becomes very simple, which is the fact that these are the radii, so they are all equal. And if you consider triangle AOB and triangle COD, you see that OA is equal to OC, OB is equal to OD, and the reason for both is this. Cool. And it's already given that angle AOB, the central angle of the chord AB, is equal to the central angle of the chord CD. Therefore, what is the postulate, folks? By SAS, we have a side, and included angle. That's important. That's why A is sandwiched between S and S. So by SAS postulate, we can say that triangle AOB is congruent to triangle COD, which means the corresponding parts have to be equal, right? Therefore, AB is equal to CD. In other words, if the central angles of the chords are equal, or if the angles subtended by the chords at the center are equal, then the chords themselves are equal. Very simple. Fantastic. Let's move on. I know we might just be proving certain facts here, but once we start applying these in various problems, it gets very interesting, folks. Cool. So we are just learning the tools needed, and then when we start applying them, we start playing with those tools. It's going to get very interesting. So let's move on. Now, we looked at equal chords and the angles that they subtend. Now, let's look at equal chords, AB and CD, and let's see what happens to the distance from the center to the chord, right? And we discussed this some time back on what do we mean by the word distance in geometry. Okay, whenever we use the word distance, specifically of a point, distance of a point from a line, then we are referring to shortest distance always. Am I right, guys? So the minute we talk about shortest distance, let's say this is the point P where the line from the center touches the chord is P, and for this, let's say it's Q. We know that this shortest distance is perpendicular to the line. Do you remember that, guys? We took a line, we took a point somewhere, an arbitrary point, and we tried connecting the line and the point in various ways, and then we figure that of all those lines that can be used to connect a point O to a line UT, let's say, is the one that is shortest is the one that is perpendicular, right? Okay. So what can you say about OP and OQ if AB and CD were equal? Right? Let's see. Just connect OA, OB, OC, and OD, right? Now, you will observe that equal chords are equidistant from the center, which means the distance, shortest distance from the center to the chord AB, the shortest distance from the center to chord CD, these two distances are equal. Shall we prove it, folks? So let's say, oops, hold on, sorry. Okay, so let's begin the proof. So we have given, what is given? We begin with the fact that the chords are equal, AB is equal to CD, O is the center. We're not talking about the distance of the chord from any random point. It is from the center, okay? So O is the center. What do we need to prove? We need to prove that OP is equal to OQ. The distances indeed are equal from the center. Okay, so by the way, when we are writing this, it is assumed that we dropped a perpendicular we dropped perpendiculars. We dropped perpendiculars from O to the chords AB and CD respectively. And those are the points that we marked as P and Q. I hope you're joining all those facts together. Okay, so let's now get into the proof. Guys, can you pause here and see if you can prove it yourself? How can you prove that OP is equal to OQ? Okay, cool. So now in this case, please consider the triangle. I'm just shading the triangles here. Okay, let's consider these two triangles, the ones that I've filled with these dots. So let's consider triangle OPB and triangle OQD. Okay, first and foremost, you see that OB and OD are equal. They are the radii of the circle. Now, you also observe that these angles OPB and OQD or even OQC, they are all 90 degree, right? Because we dropped a perpendicular. And why did we drop the perpendicular? Because we were talking about the distance from the center, and the distance is always the shortest distance of a point from a line. Cool. What are we left with? Now, please connect the dots. In the previous class or the previous video, we looked at the fact that a line that is dropped perpendicular to a chord from the center of the circle, let's assume we have a chord. When we drop a perpendicular from the center to the chord, we observed that it bisects the chord. In that case, right, first and foremost, the line OP bisects the chord AB. Hence, I've marked these two to be equal. Now, the line OQ bisects the chord CD. So, I have marked it like this. Okay, at the end of the day, it's just bisecting the individual chords. From there, let's see how OP becomes equal to OQ. Let's just list everything down. So in these two triangles, we see OP is equal to OD because it's the radii. And we see that the line OP bisects AB and the line OQ bisects the chord CD. What is the reason for both, guys? I'll just use an and here. The reason is that a line perpendicular, hang in there, I need to erase, I need to make some space. Okay, a line perpendicular to the chord from the center bisects the chord. You need to actually mention this, guys. You can't assume anything. From the center bisects the chord, right? Which means, okay, we have AP equals PB and CQ equals QD. But we already know that AB is equal to CD because it's given the chords are equal. Then can we assume half of AB will be equal to half of CD? What does that mean? Half of AB is PB and half of CD, okay, is QD. Right? So let me just round it up once again for you. We have one side that is equal. We have another side that is equal. And we know that it is a right angle triangle. Right, guys? These two are right triangles. Am I right? I know it's a little shabby. I should work better on the space on the screen. So with that, if you list that down as the next parameter, you will realize that by using the RHS criteria for congruency of triangles by RHS, triangle, let's just pause and reconfirm. We have R, which is right angle, H, which is hypotenuse, right? The corresponding hypotenuse are equal. We have right triangles and any one side, RHS, right angle, hypotenuse, and any one side, that side happens to be this PB and this, which is QD. By RHS, triangle OPB is congruent to triangle OQD. Where do we go from here? If they are congruent by CPCTC, can we see that OP is equal to OQ? So I'm marking that here. OP is equal to OQ, or equal chords are equidistant from the center. Okay, can you pause and please make a note of this? Cool? Fantastic. Moving on, as usual, can we look at the converse? Which means if two chords, okay, we have two chords, we are not assuming anything about these chords, but if it is told that, if it is told that the distance of this chord from the center are equal, then what can we say about the chords? Okay, so let's just join these two endpoints. Do you see something from this, guys? As usual, you will realize that if two chords are equidistant from the center, then the chords themselves are equal. Okay, shall we prove it? Oops, shall we prove this? So we have, just give me 1 minute. Yeah. What is given in this case is whatever was to be proven in the previous theorem becomes the given in this case, which is, let's mark this as P and Q. These are the shortest distance from the center, hence they are perpendicular, right? Okay, so it's given that AB and CD are chords. We have O as the center, and OP and OQ are perpendicular to AB and CD respectively. Does that make sense? And last but not the least, very important thing here, we begin with the fact that OP is equal to OQ. That is what we mean by equidistant from the center. Okay, so they are equidistant. We need to prove that the chords themselves are equal. We need to prove AB is equal to CD. So can you pause and try it for yourself, guys? It's very easy. It's just the reverse of what we did. Okay, cool. So now in this case, you will join OB and OD, right? And look at these two triangles, POB and triangle POPQOD. Let me just check if I mentioned it correctly in the previous slide. Okay, that's right. Let's bring it back. Okay. So here we know that OP is equal to OQ, right guys? Because it is given. These two are the radii as usual. OB is equal to OD. It's the radii. And you have, these two are right triangles. We have angle OPD is equal to angle OQD. It's given, right? Because we drew the perpendiculars, we dropped the perpendiculars to talk about, oops, what happened to my theorem? Yeah. So this third point is because it's given, right? So you will observe very elegantly by RHS, these two triangles are congruent. By RHS, triangle POP is congruent to triangle QOD. Now guys, I might you know, just write statements here and there. It's just to manage the real estate on my screen, but I would request you to write beautifully, sequentially, one below the other. It's because, you know, there is a certain way in which you need to present your answers in the exam. So I request you to write one below the other and draw diagrams neatly. Cool? Okay. So if they are equal, guys, then as an outcome by CP/CTC, what's important to observe is that PB will become equal to QD. Am I right? PB will become equal to QD. Well, I'm marking this after I've proven it. I request you not to mark something in the diagram which needs to be proven right up front, because then it can confuse you and you may end up using that as a fact, right? I'm marking it now. It's okay even if you don't mark it, because you just mark what is given. Fantastic. We've reached here, but how do we use this fact and prove that the chords are equal? Can you think about it? Okay, now this is very obvious. If PB is equal to QD, don't we see that OP and OQ bisect the chord AB and CD respectively? Why is that? As usual, a line from the center of the chord and perpendicular to the chord bisects the chord, is it not? Therefore, if PB is equal to QD, what can you say about twice PB, right? Twice PB will definitely be equal to twice of QD, okay? So all I'm saying is these parts are also equal, right? So twice of PB is nothing but AB, and twice of QD is nothing but the chord CD. Hence, we have just proved that the chords themselves are equal. If you have two chords that are equidistant from the center, we just proved that the chords themselves are equal. Okay, guys. Again, simple theorems. You just have to present what is given and what needs to be proven in a beautiful manner, and then it's basic logic. Okay, basic reasoning. What we shall do after this is quickly draw a mind map on all the theorems that we've studied so far. Okay, that way we are making a list, and we are likely to remember it for a long time. Okay, cool.